In the previous videos, we've looked at how to locate and classify the local extrema of a function. So now we're going to turn our attention to global extrema. You might remember how to find global extrema in single variable calculus at least on a closed interval, by looking at all the critical points on the closed interval as well as on the endpoints, on the boundary of the interval. And that followed from something called the extreme value theorem, which is also true for multivariable functions. And so that's going to be our starting point in finding global extrema. So the extreme value theorem says the following. So it says that if I have a function, f of x, y, and it is continuous on a closed region, a closed bounded region. I'd just mention what closed means. I don't believe I've used this word. And we'll see in an example what I mean by this. But closed really just means it's containing all of its boundary points. And I sort of talked about an open region earlier. Was one that sort of the interior point of a region was something not on the boundary. So a closed region is just simply one that contains all of its boundary points. Right? So if a function is continuous on a closed bounded region, then f of x, y attains both a global min and a global max on that region. So in single variable calculus, the extreme value theorem simply said that if f is continuous on a closed interval, and that would be a region on the real line that contains all of its boundary points, namely the two endpoints of the interval, then it attains both a global min and a global max on that interval. So this is just a natural extension of that to multivariable functions. And so just a little bit on the idea of closed. We're not going to get too much into this topological nature of the regions in the plane. But for example, if I want to talk about some point in some region in the plane that is a rectangle, right? The boundary of the rectangle would be the four sides of the rectangle, those four segments in the plane. The interior, of course, are the points inside. Right? So this would be all the points on the interior. And the sides itself are the boundary. And so this would be a closed region as long as every point that's actually on the boundary of the rectangle is included. Right? Sometimes we might consider regions, and we'll do this later, where we have just the interior of the rectangle, and I'm going to denote that with the closed line. So the region in this second example would be ones where I want every point inside but not on. Right? And so this first example I drew would be a closed region because it contains all of the boundary points. This example is not closed because it does not contain the boundary points, all of the boundary points. And even if in the second example, even if I closed up some of it, maybe I'll go ahead and fill in 3 of the sides. This is still not closed. It needs to contain all boundary points to be closed. Right? So it has to contain every point on the 4 sides of that rectangle. Right? So now that we have the extreme value theorem at our disposal, we can quite easily find global extrema of functions on a closed region. Right? And so we're going to mimic exactly what you did in Calculus 1. In Calculus 1, what you did on a closed interval is you found all the critical points inside the interval in the interior. You took the 2 endpoints and you substituted all of those values into the function, and you made a list of function values. And because you knew there was a maximum and a minimum on that closed interval from the extreme value theorem, you knew that whichever function value was the largest had to be the maximum, the global maximum of the function, and whichever function value was the smallest had to be the global minimum. And so the exact same process works here. So what we're going to do is first we're going to find the critical points in the interior of the region. Then we're going to find the local extrema of the function f on the boundary of the region. And then we have a list of points. And so once we have that list of points, we're going to calculate the values of fxy at all the above points, the critical points in the interior, and the local extrema on the boundaries. And of all these values, the largest value is the global max. And the smallest value is the global min. So let's look at an example. So let's say we wanted to find the global extrema of the function f of xy equals 8 minus x squared minus y squared plus 4x plus 4y. And we need a closed region. So on the triangular region, with vertices 0, 0, 4, 0, and 0, 4. All right, so we have our multivariable function, and it's on a closed region. It's on a triangle, so we're going to consider that to include the endpoints, or the boundary points, the three sides of that triangle. And so just because we're going to need it, let's go ahead and sketch this region in the plane. All right, so I just need the x and y axis. I really just need the first quadrant. And so our region, we have our 3 points. We have 0, 0, which is the origin. We have the point 4, 0, which is our point out here. And we have our point 0, 4, which is 4 units up on the y-axis. And so we have our point there. And so we end up with those three segments as lengths or sides of our triangle. And so we have this triangle right here. Right? And we have, of course, all the points inside of that triangle. Now, later on, we are going to need to know the equations of all 3 of these sides of the triangle. So while we have the picture, let's go ahead and write that down. All right, 2 of them are really easy, and 1 of them is just a little bit harder, but not much. All right, so we know the 2 sides are the x and y axis. So we know the x-axis is y equals 0. And we know the y-axis is x equal to 0. So that's pretty quick. And the third one we know is a line, and we know that it has a slope of -1. So it's going to be negative x. And of course, in this case, we can clearly see that the y-intercept is 4. So this is going to be y equals negative x plus 4. Right? If we didn't know the y-intercept or the slope, obviously, it wasn't obviously in this case, then we could just find the 2 points on the line, or we know the 2 points on the line, we were given those, and you could just find the slope of them and then point slope form and all of that algebra stuff. That's fun, and you can do it pretty quickly. But we're going to need those equations later, so we might as well just write them down now. All right, so first step of the process is to find all of the critical points on the interior of the triangle. All right, so we just had a whole video on doing this. So we're going to find our first derivatives. So f sub x of our function is going to be negative 2x plus 4. And we want to know when that is equal to 0. And so that will only equal 0 when x is equal to 0. Or I'm sorry, x would equal to 2. And we can solve that equation pretty quickly. All right, so now we also want to look at f sub y and compute the derivative. And at this point, before we do that, I noticed that I actually copied down one part of the function incorrectly. It has not changed anything so far. It won't change anything so far, so I want to go ahead and do that really quickly. So I wrote plus 4y, this last term. That should actually be 2y. All right, it's going to make the algebra work out a little bit nicer. So f of xy, the original function, that last term should be plus 2y, not 4y. But notice I have not used that term yet. So that has changed nothing else that I've said in this video. All right, so now returning back to f sub y, this is where it would have changed something. F sub y is going to be negative 2y plus 2. And I want to solve that when that is equal to 0. And so that gives me a value of y equal 1. Right? And so we only have one critical point for this particular function, and that is the point 2, 1. And it is often important to check. We do want, if you go back to look at the steps of our process, we do want to look at only critical points that are in the region, in the interior of that region. And of course, point 2, 1 is right here in the region. So it is definitely inside that triangle. And so we will want to consider that. Sometimes when they're more complicated functions, we will have multiple critical points, and we will have to exclude any that are not in the region. So it's worth going back and checking to making sure that the critical points we find are actually in the region that we're considering. Had this been a smaller triangle, if we were looking on the triangle, say between 1, 0 and 0, 1 as the two vertices, this critical point would not be considered. It would not be inside of that triangle. Now, while we're here, we can go ahead and compute f of 2, 1. This is the last step. This is one of the values we're going to have to compute. So we're going to have to compute f of 2, 1. And when we take x is 2 and y is 1 in the original function f of xy that's at the top of the screen, and again, remember, I changed that to be a plus 2y at the end, we get a value of 13. Right? So this is going to be a number we want to remember, or this is a value we want to remember, that f of 2, 1 is equal to 13. So now that we found all of the critical points on the interior, the next step is to find all the local extrema on the boundary of our region. Our region here is a triangle, which consists of 3 line segments. And so what we're going to have to do is find the local extrema on each of the line segments individually and add all of those values to our list. Right? And so if we look at the first side of our triangle, this would have been the side on the left side. This is going to be along the y-axis, so that's x equals 0. All right, but we don't want the entire y-axis. We only want a particular segment. So we only want y between 0 and 4. Right? So this equation, x equals 0, and this inequality, 0 less than or equal to y less than or equal to 4, describes one side of the triangle. Right? And so along that side, the function f of xy that we originally started with, we can go back and replace x with 0. We get the function 8 minus y squared plus 2y. Right? So along this side of the triangle, this is the function that we have. And we want to find the local extrema. And so we know how to do that. This is now a one variable function. Right? So we can differentiate this, and I'm going to use the prime notation because we're thinking of this as a function of y when x is fixed at 0. And so the first derivative with respect to y is negative 2y plus 2. To find the values there, we want to set that equal to 0 and solve. So that'll give us a value of y equal 1. So y equal 1 is our only critical point on that side of the triangle for our one variable function, x8 minus y squared plus 2y. And so we know that on that side, the extrema has to occur either at y equal 1 at that point or at one of the two endpoints. The endpoints on this region are, of course, the origin and the point 0, 4. And so while we're doing this right now, we can make a list of the function values at our 3 points that we have. And so f of 0, 0. And now in this case, we are using our original function. So f of 0, 0 will be equal to 8 if we replace x and y with 0. In fact, we could even use the f of x, y at the top because all of these are going to have an x equal to 0. So we could use the 8 minus y squared plus 2y if you like. F of 0, 4 will be 8 minus 4 squared plus 2 times 4. That's 0. And f of 0, 1, that's the one we get from the critical point y equal 1. We substitute y as 1 in there. We get 9. And so these are values that we're going to add to our list. Remember, we already have one value on our list. We have f of 2, 1 equals 13 from our critical point. And now we have these 3 values here that we can add to that list. So now this gives us everything on our one side of a triangle, and we're going to repeat this process for the other 2 sides. So if we go along the bottom of the triangle, that's on the x-axis. So we're going along the y equals 0 and from 0 to 4 with x. Right, so along that, we have our function f of x, y, which is going to equal 8 minus x squared plus 4x. Right, we're letting y be 0 in this case. This is a function of one variable, and so we can substitute, or so we can apply single variable calculus to it. We can compute its derivative. And this will be negative 2x plus 4. We set that equal to 0 to find the critical value, and we get one critical value. We get x equals 2. And so this gives us the point 2, 0 is going to be a point we need to check. And we also need to check the endpoints of our side, which would be at 0, 0 and at 4, 0. And so we're going to take all of these 3 points and evaluate them for our function f. Okay. Now notice we've actually already computed f of 0, 0. That was one of the endpoints of the other side. And so in fact, we're going to get all the sides, of each of the vertices of this triangle, we're going to be counted on 2 of the sides. And so I actually don't need to compute f of 0, 0 again. We've already used that. We've already checked that one. It's in our list. So I'm going to go ahead and cross that one off, although if we hadn't checked it yet, we would have to check it. All right, and so we do need to check f of 4, 0. And f of 4, 0 will be 8. And we also need to do f of 2, 0. And f of 2, 0 turns out to be 12. Right, so I'm skipping over the arithmetic here, but it is quite literally just plugging 4 and 2 into our function for x and 0 for y and doing the arithmetic. And so we get these 2 values that need to be added to our list. So now we have a total of 6 values if you exclude counting the value at the origin twice. So we have 6 different values to check so far. And there's one side of the triangle remaining. So the third side of the triangle we saw earlier was given by the equation y equals negative x plus 4. And we need to describe just that segment. And so this can be done in a couple different ways. Probably the easiest way is saying that I want both x to be greater than 0, as well as y being greater than or equal to 0. All right, I'm really just looking for the part of that segment that's in the first quadrant, or sorry, the part of that line that's in the first quadrant, including on the axes, and so that you could describe that as saying x and y are both greater than or equal to 0. And so on that particular segment, right, I have my function f of x, y. Well, what we're actually going to compute here is f of x comma negative x plus 4, or maybe I'll write that as 4 minus x. Make it a little bit simpler. So we want f of x 4 minus x. And so when we do that, we're going to get 8 minus x squared minus 4 minus x quantity squared plus 4x plus 2 times 4 minus x. And if we go through and expand and simplify everything in sight, this becomes negative 2x squared plus 10x. All right, so that's just algebra. All right, and so this is our function. And so again, we want to kind of do the same thing that we've done on the other sides. This is just a little bit more complicated to get into the right form. We want to take its derivative. So f prime of xy. Of course, we only have one variable here. So this will be negative 4x plus 10, and we want to set that equal to 0. And so we see that this is going to be equal to 0 when x is 5 halves. Right? So we get this one critical point. Right? And so this ends up being the point 5 halves. And then we have to be careful here. Our y-coordinate is given by y equals 4 minus x. And so a y-coordinate at 5 halves on the side of the triangle would actually be 3 halves. And so this is 4 minus 5 halves. This was our y value on that particular side of the triangle. So that's where that 3 halves came from. And we also have the endpoints to check. So we have our endpoints. The endpoints of this side of the triangle are 4, 0, and 0, 4. And notice that we've already computed the function value at each of these on our previous sides. So if we wanted to, we could do that, but I'm just going to cross them out because they're not going to give us any new information. We actually know the function value at each of them already. We already included those. So really all we need to know is we need to know the value of f of 5 halves and 3 halves. It's our only new value to consider. And so when we substitute that into our function, we're going to get 25 halves. So this is our new value to consider. So we had one critical point on the interior, and we've had 6 points that were either endpoints of our interval of our sides of the triangle, or were critical points on one of the sides. So each of those sides of the triangle had one critical value to consider, as well as the 2 endpoints. And so we have a big list of values. Right, so just to record all of these in one place, we saw f of our critical point on the interior, f of 2, 1, was equal to 13. We saw f of 0, 0 was equal to 8. We saw f of 0, 4 was equal to 0. F of 0 to 1 was 9. F of 4, 0 is 8. F of 2, 0 was 12. And f of 5 halves, 3 halves was equal to 25 halves. So using the extreme value theorem and the theory with critical points that we did in previous videos, we know the global max and the global min both exist, and they must be on this list. And so when we go through here, we just need to find the largest value and the smallest value. Right? So our largest value on this list looks like it will be 13. All right, 25 halves is actually 12.5, so it's close, but not quite. Right, so this is our global max. And notice it did occur at the critical point that was on the interior of our region, so we did need to consider that. So it is possible for a global extrema to occur in the interior point somewhere. And likewise, if we look at the smallest value here, it looks like that would be 0. And so we have a global minimum occurring at the point 0, 4. Right? So 0, 4 happens to be one of the vertices of our triangle. It was one of the points on the boundary. And so we have this this possibility as well that the global extreme value will occur at one of the boundary points. In this case, it occurred at one of the end points of one of our segments, but it is certainly possible with a different function that the global min or max could have occurred at a boundary point, but not one of the endpoints. And that's why it was important to compute on each of those segments the local extreme values for that function of one variable when we were able to substitute in the values for the other variable. And so sometimes those will also come up with the global extrema for a particular function.